Okay. Got some visitors today for the video. Today in class, what we did is we took sample sizes of 5, 10, and 25 of your pennies, and you found averages. And if you remember, every one of these X's was your average, and I graphed them. And we noticed as the sample size went up, the distribution got, some people said smaller, the standard deviation gets smaller. The law of large numbers says, we should get closer and closer to the true value. If you had a very oddball penny in your group, as the sample size goes up, all the other pennies kind of override that value, and that's why we get closer and closer and closer to a true value, okay? And you notice too, as the distribution starts to take on kind of a normal looking shape. We found a green arrow for all three, and that green arrow was the mean of our distribution. All right, so this green arrow, I would label it as the mean of means. It's the mean of X bar, because all of your numbers here are X bars. Every single one of these, this is your X bar value. Remember, X bar coming from your data. So this is the mean of X bar. This is the mean of a distribution of X bar. Just how before we had a mean of p hats, we now have a mean of averages. So we're not talking about proportions, we're talking about numbers that you can take an average of, like someone's height. All right? And so that's what we did in class. We also laid the pennies on the floor. And if you remember, when we laid the pennies on the floor, the overall shape of the distribution was skewed left, in which this was like 2013, and down here was around 1950. Okay? And what did we notice? We noticed that the mean of the distribution on the floor was around 1993. And lo and behold, that was the same mean that we had when you guys sampled. And the biggest thing that you had to get from today was the fact that no matter what the shape of the population is, again, this is our population, if we sample appropriately from it, our distribution of averages will be fairly normal, and its mean should be very close to the true population mean. Again, this green arrow would be the mu of the population, no matter what shape this population is. All right? So vocabulary-wise, we call this a distribution of means, and this is our distribution of our population. All right? Well, that's chapter 18. That was the second half, which leads us to chapter 23. So we're going to move right into chapter 23. So chapter 23 is about inference, or what do we know about means or averages. All right? So some common vocabulary that we're going to start with. First, sampling distribution for means. So it is a distribution of means. It's a distribution of X bars for a certain size n. Okay? N can be whatever it wants to be. And if you take a certain sample size and you find an average and you did it over and over again, it would look like one of these. And this is a distribution of averages, a distribution of means. Now, sometimes they talk about a distribution of your sample. That's taking your 25 pennies and graphing it just for you. What would that look like? Well, what's really important to remember is graphing your one data set, your 25 pennies, the distribution should mimic the population. If you took your graph, it should be a small version of this. This would be like your 25 pennies. You have more from recent years and less from earlier years. So vocabulary-wise, sometimes they'll talk about a distribution of means or a distribution of your sample. You need to know the difference between the two. The big stats theorem that you saw in action is called central limit theorem, or CLT, central limit theorem. And this is what it says. The sampling distribution of means, so the graphs that we just made today, is approximately normal as n gets larger. You notice as we went from 5 to 10 to 25, it started getting more and more normal looking, okay? Regardless of the shape of the population. Our population was skewed. We don't care. A distribution of means will be approximately normal as n gets larger. Now, its mean of means, this was our green arrow, should be very close to the true population mean, and ours was. And now here's the other kicker. Its standard deviation will be very close to the standard deviation of the population divided by the square root of n. So just like before, if you want to cut standard deviation in half, you bump up sample size by a factor of 4. You want to cut standard deviation to a third, you bump up sample size by a factor of 9. But same formula. In terms of we apply the n on the bottom under a square root. Okay? So we take the standard deviation divided by square root of n. Alright? So central limit theorem again says that the distribution of means should be a fairly normal. As long as n gets larger, it gets more and more normal looking. Who cares what the shape of the population looks like? The mean should be close to the true population mean, and the standard deviation should be the standard deviation of the population divided by the square root of n. And so, as long as we know that that's true, we can do confidence intervals and hypothesis testing. Now, in order to do those, we still have to make some conditions. And so, here are the conditions for both confidence interval and hypothesis test. They really don't change for a single sample. First of all, just like before, we have to have randomization or representative sample. Just like before, we have to have independence, and we have to have population bigger than 10 times sample. It's no different. Same thing as before. The last condition, though, is different, because we used to do n times p to make sure they're bigger than 10, because we want to make sure the sample size was big enough. Now I'm going to ask myself, is my sample size large enough for the shape of the population? Okay? So, if my population is skewed, my sample will mimic it. And because of that, I have to make sure that I take a big enough sampling size if there's skewness. Because what if I got a penny from like 1930 and I only took a sample size of 5? It would make my average way low. So depending on the shape of your population, you'll have some options here for the last condition. So, is my sample size large enough for the shape? So first bullet, if the population is fairly symmetric, so if the population has itself a fairly symmetric distribution, a sample size of 5 is fine. Hey, sample size 5, we can use this. We're good to go. We can do a confidence interval or a hypothesis test for means. If there's some slight skewness with no outliers, okay, has some skewness without any outliers, a sample size of at least 25 will start to work. All right, that was like our pennies. We didn't have any outliers. We had some skewness. All right, but you're going to need at least 25 there to override any unusual features that you have in your own data. Now, if your sample size is at least 40, we're okay no matter what the shape of the population is. So you kind of got to ask yourself, what does the population look like? And according to that, how big of a sample do I need? Now, when we started this, you didn't know what the shape of the population looked like. But if I were to make you graph your pennies, we know that the distribution of your sample should mimic the population. And because of that, to answer this last condition, what do? Since your data mimics the population, you must graph your data if you have the data values. Because it will give you a small snapshot, like Snapchat. a small snapshot of the population. So your graph will tell you whether or not you can use 5, 10, or 25. Otherwise, you need to know something about the population you're pulling from. If I'm talking about head circumference of males, I know those are going to be approximately normal, right? But if I'm talking about the number of spines on a spotted toad, I don't have a clue, all right? So if you meet all the conditions, we say it's okay to do a one sample T, and now it's either a test or interval. And why a T? We got a new letter coming tomorrow in class, and we say sample instead of proportion because we're working with means. So that's it for today's video, because tomorrow in class, since this is really new, we're going to then figure out how we get into the T. Where does this get into? It gets into our confidence interval, all right? And because of this T business, I'm going to have to show you in class how that works tomorrow. All right, that's it.